Hello and welcome to Chemistry with Dr. Clark. In this video, I'd like to talk about heterogeneous equilibrium expressions. A heterogeneous equilibrium occurs when you have reactants and products that are not the same phase. So you may start out with a solid reactant and a liquid reactant and end up with a gas product and an aqueous product. Now you can have homogeneous equilibrium expressions. A homogeneous equilibrium is where everything has the same phase or state. So if you start with gaseous reactants, you end up with gaseous products. If you start with aqueous reactants, you end up with aqueous products. So homogeneous, the state stays the same throughout the whole thing. Heterogeneous, you get a mixture of solids, liquids, gases, and aqueous. If you are looking for homogeneous equilibrium expressions, I do have a couple of videos that talk specifically about that. It talks about how to write the equilibrium expression and then how to do calculations with it. So if that's what you're looking for, you might want to pause this video and take a look at those. I've got the links in the description below. But if you are looking for a heterogeneous equilibrium expression video, you're in the right place. So if we do a quick review of what an equilibrium is versus the equilibrium expression. Okay, so this is a very general equilibrium. It talks about some reactants turning into some products and then the products turning back into reactants. The capital letters represent the chemicals. The lowercase letters represent the coefficients used to balance it. So if we pull out an actual example, let's say that we would like to talk about H2 gas reacting with Cl2 gas in equilibrium with 2HCl gas. Now, I realize that this is a homogeneous equilibrium, but to start the discussion, it's probably easiest to start there. Okay, so for this one here, the three chemicals are H2, Cl2, and HCl, right? That would be my capital letters. And the lowercase letters are the numbers used to balance. So to balance this, I'd have a 1, and a 1, and a 2. An equilibrium expression talks about putting the concentrations of the products in the numerator and the concentrations of the reactants in the denominator. Okay, so products on the top, reactants on the bottom. These square brackets here do refer to concentration, right? I mentioned that here because this whole expression is all about concentrations. Do you know the concentration of the reactants? Do you know the concentration of the products? Okay, so it'll be concentrations of the products in the numerator, concentration of the reactants in the denominator. The numbers that we use to balance, the coefficients, they become powers in this expression. So if you have A of A is the chemical, little a is the number, that becomes the power. Maybe a little easier to see it in an actual example. So if we write our equilibrium constant, KEQ, okay, we're going to put products in the top, right? C and D are products, products go in the top. Here we only have one product. The only product is HCl, so HCl. Now, I could know a lot of things about the HCl. I could know the number of moles, or its volume, or its mass, right? There's a bunch of things. But the one that I'm going to focus on is concentration. And in order to tell everybody that concentration is what I'm focused on, the way that I'm going to show that is by putting square brackets around it. Square brackets mean concentration. Now, there was a 2 in this equation, right? In order to balance it, I had 1 to 1 to 2. Because there's a 2 here used to balance it, the power in the equilibrium expression will be a 2. You take the coefficients and turn them into powers. Divided by. Your reactants go in the bottom, the denominator. Now I do have 2 reactants, so let's deal with them one at a time. The first reactant is an H2. So my first reactant is an H2. I am focused on concentration, so to tell everybody that concentration is my focus, I'm going to put square brackets around it. And when I balance this equation, there was one H2, therefore the power here will be 1. Now let's move on to the second reactant. The second reactant is a Cl2. Again, I want to tell everybody that it's concentration, so I use square brackets. And again, there's a 1 here that was used to balance it, and that 1 is going to become my power. Now, I don't think I emphasized it yet, but if you have more than one product in the numerator, or if you have more than one reactant in the denominator, you are going to be multiplying. There's a multiplication there. So because I have 2 reactants, they will be multiplied. Now, you have to be careful of that, because when you wrote your original chemical reaction, your equilibrium, there was a plus in between the reactants, and there would be a plus in between the products. But when you put it in the equilibrium expression, you get multiplication between the reactants, and it would be a multiplication if you had more than one product. Okay, so be careful of that. Now, this entire thing, this whole thing that we've written, is an equilibrium expression. Okay, it's an expression. It's a way of calculating the equilibrium constant. Now, the equilibrium constant, that's this thing right here, the KEQ, is my equilibrium constant. Now, the reason why we call it an equilibrium constant is because for this equilibrium, this number will be a constant. Okay, so let's say that you know the concentration of HCl, you know the concentration of H2, and you know the concentration of Cl2. Okay, let's say you know them. You put them in the equation, you do the calculation, and you calculate your K. Let's say that you change them. Let's say you add a little bit of HCl, or you add a little bit of Cl2, you add a little bit of H2. Equilibriums are very neat because what they do is they self-adjust. If you throw in a little bit extra of any of these chemicals, the reaction will readjust itself so that it reachieves equilibrium. Now, when it reachieves equilibrium, all of these concentrations will be slightly different because you messed with it, right? You threw something in. So you'll have a slightly different concentration of HCl, a slightly different concentration of H2, and a slightly different concentration of Cl2. But when you put it into this formula, you'll still get the exact same value of K. The equilibrium constant will be the same. And that's the beauty of the whole thing, right? You can mess with this equilibrium however you want by adding or removing things. It'll always readjust itself so that the numbers that when you put them into this formula will always give you the same value of K. That's why we call it an equilibrium constant, because it stays constant. Now, depending on what course you're in or what worksheet you're working on, it's not always called KEQ. Okay, here I've called it KEQ for equilibrium constant. Sometimes they are simply referred to as just K, and sometimes it's referred to as KC. C standing for the fact that this whole thing is done with concentrations, right? This is concentrations, that's why we use the square brackets. So sometimes it's called K with a subscript C. So depending on what your worksheet or your class is doing, you kind of have to go with the K that you're presented with. So if you're being taught about KEQs, then it's all KEQs. If you're being taught that it's just Ks, then you go with Ks. If you're told that it's a KC, then you go with KCs, right? You go with what you're given. Now for this one here, like I say, this is a homogeneous equilibrium. And in a homogeneous equilibrium, where everything is a gas or everything is aqueous, you put the products on the top, you put the reactants on the bottom. You use the numbers that are balancing the equation as powers. Now, the minute that you get into heterogeneous equilibriums, now you start to get solids and you start to get liquids. And the rule is, if you have something that's a pure solid or a pure liquid, they are omitted from this equilibrium expression. This equilibrium expression loves gases. See how these were all gases? Loves gases. If they were all aqueous, again, it would look exactly the same. This equilibrium expression loves aqueous. But this equilibrium expression hates solids and hates liquids. Okay, those, you're not allowed to have them. You have to just leave them out. Now, let's talk a little bit about why we want to leave them out. Okay, so let's say we have this equilibrium right here. It's talking about gold solids, plus chlorine gases being in equilibrium with gold 3 chloride. So if I look at this equilibrium, I can see that it is a heterogeneous equilibrium, right? Solids and gases and gases. So I can write an equilibrium expression, right? So I can say KEQ is products over reactants. So if I look at my first product is gold 3 chloride, so AuCl3. I want to tell the world that this is all about concentration, so I'll put in my square brackets. And because there is a 2 used to balance the equation, that's going to be to the power of 2. Now let's talk about the denominator. The denominator is all about the reactants. So your first reactant is gold solid. So let's write it in. So there's my gold. Put it in square brackets to tell everybody that it's concentration. I use the 2 to balance the equation, so this will be squared. I have a second reactant. The second reactant is Cl2. Again, I'll put square brackets around it to tell everybody that it's concentration. And I use the 3 in front of it in order to balance the equation. So this is power of 3. Because you have 2 reactants, they are actually multiplied together. Now, what I'm telling you is that if these had all been gases, then the equation would look exactly like this. If these had all been aqueous, then the equilibrium expression would look exactly like this. But because you've got a solid, the solid really shouldn't be there. So this Au squared, this thing, really shouldn't be there. It should be gone. So if I cover it up, the real answer would be KEQ equals gold 3 chloride squared on the top and Cl2 cubed on the bottom. That's what the answer should look like. So if you have a solid or if you have a liquid, you just leave them out. That's the rule you have to remember. Now if we take a minute, we talk about the why. For this equation here, we've got the constant over here on the left, and what we assume is everything on the right is a variable. Everything on the right can change. Okay, so if we come back to the original example I had here, remember how I said that if you knew all these concentrations and you put them in, you'd get the equilibrium constant. And then I told you that if you added or removed something, right, you messed with the concentrations, they would all readjust themselves so that they would still add up and multiply and divide and do their thing to give your equilibrium constant. What that's telling you is that the concentration of HCl can change. It's variable. The concentration of H2 can change. It's variable. The concentration of Cl2 can change. It's variable. We like to have things over here that are variables. Think math class, like x's and y's. They can have all kinds of different values. And we like to have our constant over here. If you take a look at this, what I'm going to show you is that if you have a solid or a liquid, that concentration is actually a constant. Okay? So let's do like 2 different examples. Let's say that you've got your Cl2 gas in this bottle right here. Okay, so that's my Cl2 gas and my Cl2 gas. If I want to calculate the concentration of Cl2 gas for this calculation here, right, because I need to know the concentration, I can use the moles and the volume to calculate concentration. Okay, so for this one here, the concentration is moles over volume. So the concentration would be 1.00 moles divided by a volume of 0.500 liters. Right? Because concentration is just the number of moles you have divided by the volume. So if we pull out our trusty calculator, 1 divided by 0.5 gives me 2. So I would have a concentration of 2.00 moles per liter. Now, the really cool thing about gases is that you can squeeze a lot of gas into a really small place. So let's say that instead of putting 1 mole of chlorine in this container, let's say I've decided to put 2 moles of chlorine in this container. I've decided to put twice as much in, right? It's like pumping up your tire on your bike or your car. You can keep pumping and keep adding air, and the volume doesn't really change, right? The size of the tire on your bike or the size of the tire on your car doesn't really change, but you're still squeezing gas into it. So for this little bottle here, the volume is the same. It's still 0.5 of a liter, but now I've squeezed in twice as much chlorine, right? I used to have 1 mole, and now I have 2. So if I calculate the concentration, moles over volume, so my concentration would be 2.00 moles divided by 0.500 liters. And so my concentration would be 2 divided by 0.5, 4 moles per liter. So when I talk about the chlorine gas, the concentration of the chlorine gas is able to change. Because for a gas, I'm able to keep the container the same size, but change the amount of gas that goes into it. Now, aqueous would be similar, right? Think about the last cup of tea or coffee that you had. Okay, so you have your cup, and it has a certain amount of water in it, and let's say you put in 1 spoonful of sugar. That 1 spoonful of sugar will dissolve in your tea and coffee. So you have 1 teaspoon of sugar per cup of coffee. What about if you really like your coffee or your tea sweet? Let's say you put in 4 teaspoons. You still have the same volume. You still have only 1 cup of tea, but you've added 4 times as much sugar. So the concentration would be 4 times as much, right? 4 spoonfuls of sugar in a cup rather than 1. So if you're talking concentration of gases or concentration of aqueous, they are variable. They can change. But if you talk about a solid, okay, let's say you have a block of gold. Okay, so you woke up and there's like this block of gold sitting next to you. I'm telling you that it's 1 mole, and I'm telling you what the volume is. So you can calculate the concentration, moles over volume. So the concentration is 1.00 moles divided by a volume of 0.01021 liters. And again, we'll haul out our trusty calculator. 1 divided by 0.0102 gives me 98.0 moles per liter. You know the number of moles and you know the volume. Okay, so that was this morning. This morning you woke up and the first thing you saw was a block of gold sitting next to you. And you're like, woo, block of gold. You wake up tomorrow morning and you don't see 1 block of gold. You see 2 blocks of gold. And you're like, wow, I am the luckiest person ever. Gold is just appearing magically while I'm sleeping. Well, if you've got twice as much gold, you should have twice as many moles, right? You went from 1 mole to 2. But unlike the gas being contained by a container, if you have twice as much gold, it should take up twice the volume, right? If your original volume was 0.01, your new volume should be 0.02, right? If you have twice as much gold, it takes up twice as much space because it's a solid. So if I calculate concentration one more time, N over V, the concentration equals 2 moles, because you have twice as much, so you have twice as many moles, divided by 0.02042 liters. Again, twice the volume, because you got twice as much gold. If I do the calculation, 2 divided by 0.02042, it gives me the same concentration, 0.979 moles per liter. Now, this would be just a little bit of rounding error on these two. But if you've got 98 versus 97.9, they're the same number, right? They just round off to be the same. And the reason for that, you've doubled the numerator, so your numerator is double, but your denominator is also double. They're equivalent fractions, right? Think of it if you had 1/2 versus double both of them, 2 over 4. 1/2 and 2 over 4 is exactly the same number. When you're talking about solids and liquids, in order to have twice as many moles, it's going to take up twice as much space, right? Think of a glass of water. If you have twice as many moles, then you're going to have 2 glasses of water, right? It's going to be twice as much. So for solids and liquids, concentration is a constant. Okay, that's really important. So concentration for solids and liquids is a constant. All right, so if I look at my expression again, what I've got is a constant over here on the left, which is where I like my constants. I've got this, which is a gas, right? My gold 3 chloride, so that's a variable. My Cl2 is a gas, that's a variable. But my gold is a solid. This concentration never changes. It's going to be a constant. And we don't like having constants on the right side. The right side should only be variables. So what we decide to do is we decide to move it to the other side. So if it's divided here, when I move it to the other side, it becomes multiplied. So KEQ times the gold concentration squared equals AuCl3 squared divided by Cl2 cubed, right? So I kept this, and I just moved this to the other side through multiplication. Now, let's talk math. So you're in math class and your teacher's asking you to do some sort of math equation, and so you give this as an answer. 2 times 3 equals x. Okay, move it up so you can see it. So if you go into math class and you say, hey, the answer is x equals 2 times 3. Whoever gave you the problem is going to say, and, right? They're not going to let you leave it as 2 times 3, because 2 is a constant and 3 is a constant, but you can put them together and call it 6, right? Which is also a constant, right? Constant times a constant is a constant. So in chemistry, we're sort of the same, right? KEQ is a constant. The concentration of gold solid is a constant. If you've got a constant times a constant, why don't you just put them together? And that's what we do. So when we say KEQ equals, that's the equilibrium constant, but built into it is any solid or liquid concentrations, right? So it's already built into it. It's not something that you have to worry about as a separate thing. So that would be equal to concentration of my gold chloride squared divided by my concentration of my Cl2 cubed. So when we look at this, what we tell ourselves is, oh, if there's a liquid or a solid, you just ignore it. And that's what we do. We totally ignore them. But in reality, any concentration of a solid or a liquid is already built into the equilibrium constant, because the concentrations of solids and liquids are constant. So it's already built in. So when you look at your equilibrium constant, it's already got it there, right? It's just hiding. And instead of telling ourselves that every single time, it's just much easier, much faster to say, oh, if you got a solid or a liquid, you just leave it out. Okay? That's the why. So let's say that we do an example or 3. So if I take a look at this first one here, I've got a gas, I've got a liquid, and I've got a gas. If it was me personally, because it's very easy to get into the habit of just write all the products on the top, write all the reactants on the bottom, and move forward. And then sometimes it's easy to miss that something needs to be left out. So if it was me, the first thing I would do is perhaps underline this and say, hey, that's a liquid. When I write my equilibrium expression, that's not supposed to be there. Okay, so now let's write our equilibrium expression. So KEQ equals products on the top, reactants on the bottom. There is only one product. The one product would be my HBr, so HBr. Tell the world it's a concentration by putting square brackets around it. And you use the 2 to balance it, so this would be squared. Now, if you look at your reactant side, H2 is a gas. We like gases. Gases, good. So I'll put my H2 here, put my square brackets around it to tell everybody it's a concentration. We use the 1 to balance, so this would be power of 1. And the Br2 liquid is a liquid. Pure liquids have a constant concentration. So it doesn't go into my expression. What we tell ourselves, it's already built into the equilibrium constant. It's already there, built in. So we just ignore it. And this would be the equilibrium expression. The whole thing is the expression for this equilibrium. All right, let's try a second one. So if I take a look at my next equilibrium, it says I have some carbon solids reacting with some H2 gases to make some C4H10 gas. So again, I can see that there is a solid, and again, I'm just going to ignore it. Right, I'll put some lines under it to remind myself, don't accidentally include it. All right, so equilibrium constant, KEQ, products over reactants. The only product I have is a C4H10. I'll put it in square brackets to tell everybody its concentration. And there is a 1 used to balance it, so it's power of 1. Now you'll notice that when I balance equations, I like to leave the 1's out. If there's no number there, it's assumed to be a 1. So we like to do the same thing with the powers. If your power is 1, we often leave it out because if you don't see a power, you assume it's a 1. Now, if we look down here in our denominator, this is carbon solid. We don't like solids. Don't like liquids, don't like solids. So I'm going to ignore it. The H2, though, is a gas. So let's include the H2. So that's my H2. Square brackets tell everybody its concentration. And I did use a 5 to balance the whole thing, so this will be a power of 5. Now, I didn't include the carbon because it is included in the equilibrium constant, but all I have to do is remind myself, liquids and solids, leave them out. All right, let's see what happens in the next two, because these are a little bit more different. So if I look at this equation here, I have gas, gas, and liquid. Oh, don't like liquids. Liquids are not going to be part of my equilibrium. So if I write my equilibrium expression, KEQ, products over reactants, I don't actually have any allowable products, right? I've only got one product. The only product is H2O, so there's only one, but it's a liquid, so I'm not allowed to use it. So I have nothing to put in the numerator, like nothing, because the only product I have is not allowed. If that happens to you, you just put a 1 there. Because if we look back up here to these examples, would it really change this if I said it was 1 times? Right? Would it really change this one if I said it was 1 times? Right? There are 1's hiding in my numerators. I just don't write them because they don't change the problem. But if you have nothing else to put there, you put in a 1. Now, the denominator is going to go like always, right? Your first reactant is an H2. Put it in square brackets. You had a 2 to balance it, so power of 2. Your second reactant is an O2. It is concentration, so you're going to put in some square brackets. There's 1 of them, so it should be power of 1, but I left out the 1 when I balanced it, so I'm going to leave out the power of 1 when I write the expression. And if you have more than one reactant, or if you have more than one product, they're multiplied, right? They were added into equilibrium, but they're multiplied in the expression. So this one is the same as the rest, but it's a little different because you don't have actually any chemicals in the numerator, right? There's just a 1 there. All right, and let's take a look at the last one. If we look at the last one, aqueous, love aqueous. Aqueous, love aqueous. Aqueous, love aqueous. Solid, yeah, not so much with the solid. Don't really like solids. So when I write this equilibrium expression, I'm just going to leave this out. So my KEQ is going to be first product. Okay, so concentration of NaNO3. 2 was used to balance it, so that's squared. And that's my only product. If I look back here to my reactants, I have 2 of them. So the first one is an NaCl. Use the 2 to balance it, so we'll put a 2 here. Second reactant is a PbNO3 twice. You are talking concentration, so put your big square brackets around it. And in order to balance it, there was a 1 here. So really, there's a 1 as a power, but you are allowed to leave it out. Even though the reactants were added, in this expression they are multiplied. Okay? So if you're going to do equilibriums that are heterogeneous, you got a mixture of solids, liquid, gases, aqueous. What you have to remember, gases and aqueous are good. We love those. If it's aqueous or it's gas, you just put them right in. But if you have a solid or a liquid, solids and liquids, we don't like those. Those, we just leave them out. Technically, built into the K, in practice, we just leave them out. Okay? Now, in this example here, I had no chemical to put in the numerator, right? The only one that would have went there was a liquid, so I left it out. Sometimes the same thing happens for the denominator. So if it turns out that you have nothing for the denominator, you just put in a 1. So in these problems, if you have a numerator or a denominator where there's no allowable chemicals, you just put in some 1s. And that covers equilibrium expressions for heterogeneous equilibria. Now, there is another video that goes with this. I do talk about how if you know the concentrations, how do you put the concentrations in and then find the value of the K. So if that's of interest to you, again, I would encourage you to take a look at it. And as always, thank you for joining me here at Chemistry with Dr. Clark.